Hello everybody, welcome to video 13 of STA 513. This is going to be the end of the video portion of the course. I want to bring you guys to the last topic that we'll cover in 513, which is discussing, again in this case here, is to give you guys an example of longitudinal data analysis that we did in the cocaine study. So each of you guys have a NIDA, file that you've been working with. If we're using the NIDA collaborative cocaine treatment for the project, if we're using one of the other studies, then you've seen this data used in the examples of the class, but aren't necessarily, using it yourself. But that's okay. So I'm going to take you to my share screen. And we're looking right now at, this is the chapter 27 extra material. I'll show you the extra two at the conclusion of this presentation, but I'm going to jump you into all the way up to slide 62. Now, the earlier slides look at different repeated measures, analytical approaches. But to wrap this up, I'm going to give you guys an example of probably the most flexible repeated measures design longitudinal data analytic approach that we're going to that can be used in a lot of different situations. We saw before that ProcGLM can analyze the data through a method called repeated measures ANOVA. Now, if you remember with repeated measures ANOVA, it's fine. It models all the data, but in reality, it models the repeated measures as a vector and looks to see if there are separations on that vector. So kind of a vector in a vector space. We saw with the ProcGLM, there's two things it requires when analyzing that data. The first thing requires everybody to have complete data, where if you're looking at this cocaine study data, you could see that's not the case. We don't have everybody at every time point. The second thing is it fits the variance covariance matrix of the repeated measures as a compound symmetry design. So those two restrictions, in essence, restrict how we can analyze a lot of data. In any approach like this, if you ran the repeated measures ANOVA on your data, it would only retain patients who have all repeated assessments. In other words, that would make a completer sample. And so people that complete a trial are not exactly the same as the people who start a trial. And in reality, any kind of intervention study you do is going to have people that can't complete the trial for whatever reason. Now, those individuals shouldn't just be discarded and ignored. They should also still be included in the analysis. So now, what the mixed effects ANOVA does, it tries to extend the repeated measures ANOVA to account for those restrictions. So to allow people with incomplete data to relax the compound symmetry design. The big thing for us in implementing this approach is it requires the data to be what we call stacked instead of flat. When we looked at the repeated measures ANOVA, it was a flat file where different variables, different columns, if you picture it as an Excel spreadsheet, different columns represent the repeated measures. In this approach, we need the data to be stacked, where basically a row of data is the unit. In this case here, the row of data is the patient at a time point as the unit. So it differs from repeated measures ANOVA in that it reflects the compound symmetry assumption. Like we just said, the data's got to be in long or what we call stacked format. So in this case here, each row of data is a person time point. Now, as an example, what this mixed effects ANOVA model does, it models the on average difference. Well, let's say we have a main effect for treatment. The main effect for treatment looks at the on average difference in across treatment over the longitudinal period. So over the longitudinal time frame. So the big thing about this approach, it's looking at on average differences. If you looked at the earlier portions of CIDR, well, I'll show you in Extra 2, there are specific repeated measures models. One of the repeated measures model is what we call the hierarchical linear model, HLM. And what HLM does, it tries to model change over time as some kind of mathematical function of time. Linear change over time, quadratic change over time. So the HLM model is really flexible in analyzing change over time. But in this case, the mixed effects ANOVA, we're making no assumptions about the time profile. We're just saying whether or not there's an on average difference between treatments over time, or we can even extend the model to include a treatment by time interaction. So in other words, do the treatment differences vary significantly over the different time assessments? The big thing with the mixed effects ANOVA model, it's going to require time to be thought of as discrete time points. So in the cocaine study, the assessments were discrete time points. This is the month 1 assessment, the month 2, the month 3, the month 4, the month 5, the month 6, right? So they were discrete assessments. The HLM model that we were just talking about, time could be anything, it could be unique within each individual. But for us in this case here, we actually needed to be discrete time points. So this is called a mixed model because it will include treatment effects, or fixed effects rather, like treatment, month, gender. But then again, there's some sense of randomness in the fact that we have another source of variability. So we have the variability within the patient and the variability between the patient. Because again, we can think of the data as being stacked. The unit are the multiple assessments within a patient. The patients are above, and then the patients are randomized to treatments. So with this extra level, we have a source of randomness. So that variance covariance matrix, that the data is now no longer ID, has got to be modeled. And we're going to model it with the repeated line by identifying the various typical variance covariance matrix for the repeated measures. So in this case, time and treatment are treated as fixed factors. Since again, our interest in this is making an inference about specific time points. If you read the cocaine addiction paper that's on the D2L page, the course webpage, you'll see that in this mixed effects ANOVA model, a lot of times baseline is entered as a covariate, as well as other terms could be entered as a covariate. So the benefit of this approach, it allows for randomly missing observations. As long as people have at least one data point, they're included in the analysis. So unlike MANOVA or repeated measures, which requires completers, requires complete data, that is not the case. That is not the case of, that is not the case for the mixed effects ANOVA model. It allows covariates to be included in the model, where the covariate can be time invariant, like baseline, or it could actually be something time varying. Maybe, if we're looking at some effect over college semesters, it could be the student's GPA in the respective semester. So again, that is obviously semester varying. So that could be time varying. The big thing in this case is just, you need to know whether or not the covariate is time invariant, doesn't change over the repeated assessments, or time varying, it does. We fit a lot of different covariance structures. So we looked at a couple of the last lecture. Independence, which we're not going to use for repeated measures data, right? It assumes no correlation between repeated measures, which is pointless. The second one we looked at was compound symmetry, which again assumes any pair of data points are equally correlated regardless of space. Then we looked at the ones that were a little bit more relaxed on that assumption. Things like autoregressive, which assumes points closer in time are more correlated points further in time. We talked about the toplets, which again assumes points equally spaced in time have the same covariance, but no distinct pattern of what points is separating in time, how they're correlated. And then we saw the unstructured was as loose as they came. Assume separate variances each time point, and separate covariances between pairs of time points. But again, with us, our whole goal was to get parsimony. And if you remember, we looked at the chi-square test of the fit, the -2 restricted log likelihood we looked last time. You could use the AIC, the AICC, the BIC, again, whatever's written in your data analysis management plan. As I said before, the -2 RLL, the AIC, the AICC, the BIC. The last three are all variations of the -2 restricted log likelihood. So they all should run pretty similar as we start moving forward. So again, we have to keep that in mind. So we're aware of that. These methods can be translated to binary or ordinal outcome. So again, some of the stuff that you guys are seeing at the end of the categorical class, the GE is the first introduction to repeated measures. We could send that to what we saw in topic 0, the generalized linear mixed effects model, which again can be part of either categorical 2 or longitudinal data analysis. We can, while the HLM assumes a function of time, we can actually do that in a mixed effects ANOVA model layout. Usually the mixed effects model ANOVA layout baselines covariate as we end up begin the model. Again, this one does not, the mixed effects ANOVA model does not assume a linear relationship over time. It really focuses on the on average differences between the key predictor. And for us, it's the factor. In the ANOVA model that we looked at from the very beginning, the Kenton data, that was the design. In the cocaine study, it's the intervention arms. Now, one of the problems with this approach is if the relationship in the data is truly linear or polynomial, well, the methods that model change over time as a function of time will give us more power than the mixed effects ANOVA model. The mixed effects ANOVA model, by specifying, no relationship over time, we're using more degrees of freedom. And so we're basically specifying time as a category. So that requires more degrees of freedom. But, in this case here, it becomes really the big component is that we have to look at the data. We have to eyeball the data. The second problem with this approach is it requires that time variable to be discrete. So sometimes when time's considered continuous, like, weeks from randomization, sometimes people will discrete time. So round time to the nearest month, round time to the nearest week. So you just got to be aware and you got to make it clear what you're doing to the data to fit the respective model. As we said before, everything goes to modeling the data and not throwing the data into a model. So let me go ahead and show you guys this chapter 27 NIDA example. So I'm going to jump to SAS. I'm going to load this up. So this is the data from the cocaine addiction trial presentations. So you can see there we got a lot of data. We have almost 3,000 records of data. Well, show you guys what's inside it. So as you guys see what's inside it, the patient number month, that is the unit. That is the unit. The key variable we want to look at is treatment condition. And for the cocaine addiction main outcome paper, the primary outcome was this drug composite by the Addiction Severity Index. This ASI drug composite is a composite score which quantifies the individual's entire drug use, not just necessarily cocaine. And in this case here, it's a scale, ranges from 0 to 1, where higher values correspond to more drug usage. So we got that right there. I'm going to reduce this data set to this primary outcome, the treatment variable, the time variable, and then I'm going to throw in these couple covariates. These covariates, the ZM0, that's baseline drug composite, site, and this is baseline socialization. In this study, we're going to control for site since it's multi-site anyway, but the socialization and the psychiatric composite were a priori covariates. So they were decided to be covariates regardless of their statistical significance. So we got that right there. So I'm just going to show you the means, right? So in this case here, right now, the way this data is set up is the baseline month 0 is in the data set. You can see here the drug composite ranges from 0 to 1, but nobody's over 0.5, right? The maximum is 0.4615. Sort the data by month. Again, let's just take an eyeball at the data. I'll just show you guys what's going on when we look at this data. So this is the mean profile that you guys see here, right? So treatment 1's in red, 2's in blue, 3's in green, 4's in yellow. And so what you guys can see in this case, treatment 1 is the individual drug counseling. Treatment 2 is CT, cognitive therapy. Treatment 3 is what we call dynamic supportive expressive, and treatment 4 is group drug counseling. So as you guys could see, so everybody had to be using, so that's why there's this peak at the baseline. But we can see, once we get beyond the beginning, it looks like the red on average is lower than the other two. So in this setup, we said to ourselves, okay, let's model this data where we look at the on average intervention difference month 1 to month 6 and covary the baseline. Because it looks like on average, treatment 1 is superior to the other 3 treatments. So that was our initial thought process in analyzing this data. So again, if I just show you some of the big data real quick here. So you can see here's patient 1, right? Now, if we were running a repeated measure as ANOVA, we would lose this person because for whatever reason, we don't have his or her month 2 and month 3 assessment, right? These patients were encouraged to come in. Doesn't mean that they necessarily need, doesn't necessarily mean that they need to, that they need to, that they need to come in. They were encouraged either through some kind of economical incentive, but obviously their choice whether or not to come in. And you can see the same thing for patient 3. We're missing their month 2 and their month 3. Patient 5 is a good person. They came all the time, right? So again, it's, in a lot of data, these aren't machines. These aren't animals. These are people. So whether or not they attend or not, is their choice, and it could create missing data. So we need an analytical approach that accommodates the missingness of our data and still gives us accurate inference. So now we're going to reduce the data to that post baseline, right? And so you can see here in this post baseline, we have 459 patients. 459 patients who provide data post baseline. Reading the paper, you guys would see that there are 487 randomized patients. 487 randomized patients. For whatever reason, we had 28 patients become what we call randomized no-shows. They're randomized, but they said, catch you later. I don't want to participate. That's life. That's a day in the life of clinical trials that involve people. The randomized no-shows can decide to not show up. So in this case here, we're going to fit the mixed model ANOVA right here, right? So let me put the nums on real quick. So line 90 through 114 is giving you an example of fitting the main effective treatment, the main effective time, right? So right now, I'm just going to throw the baseline is the covariate. Right now, I think we're going to do that without, even though if you read the cocaine paper, there's a little bit more with the socialization and the psychiatric severity that goes on, right? So in this case here, I'm going to run this guy out, as you guys see real quick here, as the layout. So in this case here, in fitting the program on problem or in line 90 through 114, proc mixed, pointing to the data set we're analyzing. Now the class statement. The class contains anything that we think is a categorical predictor. So for us, the time's discrete. We're going to think of it as a category. The treatment variable, which is the most important, TX con, that's categorical. The one thing I have additionally in here is the patient identifier. Remember, the unit's patient month. So I'm showing SAS what that next level of the data is. That we have repeated observations within patient, which is the variable patnome. So my model statement, going to be the outcome. I'm going to have month as a categorical predictor. Let me go back to the plot. Right? So with the plot, I don't really care how the means are switching over months. Right? So you can see here, there are the means, there are the means, drop down, bounce up, drop down. What I'm really mostly interested in this mixed effects ANOVA model is the on average separation between the groups. The on average separation between groups. And as you guys can see visually, the red is separating from the others. Whether or not that's significant over the longitudinal time frame, we're about to find out with how we model it. So in this case here, we're going to go ahead and model it right now with the repeated line. So now, remember with the repeated line, the comment's showing you the generic layout, right? So in this case here, well, let me just run down this line. So here's our model statement, the time, the variable of interest, treatment condition, where we're trying to see if there's an on average difference between the treatments over the longitudinal period, and then the covariate. So we're treating the baseline as a covariate, sort of just like in ANCOVA. because again, when we look at the data, at baseline, the baselines aren't significantly different, but they are different. So, remember, like we said with ANCOVA, covariant to baseline basically evens these things up. And if you think about it, the red is kind of starting out the worst, right? And they drop down the quickest. So, it kind of evens things up, kind of like a fair race that we end up seeing here. So now we start modeling this. This is the generic line to model the variance covariance matrix. So we got the repeated line. In the repeated line, we put the time indicator here. That's if you have a time variable. If you don't have a time variable in your data, SAS is going to assume that each repeated row is the next time point. So without a, quote, time variable, it's imperative that your data is sorted. We have a time variable, so you should use it. The type, the form of the variance covariance matrix, and then subject, which tells SAS which variable identifies where the repeated measures are within. So for us, repeated month, right? That's telling SAS each month is the month indicates the time points, right? So in this case, you don't need the data to be sorted. SAS will end up realizing, okay, month incrementally, or how it's ordered via the class statement shows you the ordering of the repeated measures. The type equal UN, right? And then the subject equal Patno. We're going the biggest first. And now I'm going to show you guys a couple other ones besides the ones we talked. Independents were thrown away, right? We talked about compound symmetry. We talked about toplets. Now, and we talked about autoregressive. Now, if you remember with these three, what it assumed, it did different things with respect to the covariance between the repeated measures and other. But those three structures all assumed an equal variance at every time point. An equal variance at every time point, every repeated time point. So it would assume equal variance at month 1, month 2, month 3, month 4, month 5, month 6. Compound symmetry, heterogeneous. Autoregressive, heterogeneous. Toplets, heterogeneous. That heterogeneous allows or fits unequal variance at every time point. So it relaxes at equal variance at each time point. The nicety about the equal variance each time point is it quantifies a pooled variance. But if that's not truly how the data is behaving, well, you need to relax that assumption. So let's go ahead and run this and see what we have. So when we fit this model here, you can see real quick, I'm just going to look at the bottom. We see a significant effect due to month. So regardless of intervention, the on average mean at each month is not the same, with each one significantly separating from the others. Here's the treatment effect, just barely non-significant. So based on the available data, we do not have sufficient evidence that the on average difference in ASI drug composite significantly varies across the 4 treatments over the longitudinal period. The baseline significant, so in other words, we see a significant relationship with baseline depression with average baseline usage with average usage. Here's the variance covariance matrix. The unstructured, UN11, the variance at time 1. UN22, the variance at time 2. UN33, the variance at time 3. UN44, the variance at time 4. UN55, the variance at time 5. And UN66, the variance at time 6. When you look at these, I'll point out this one. This one saying us that is quantifying the covariance between time 4 and time 2. Now for us, time 4 is month 4. Time 2 is month 2. So UN 5.1 is the covariance between month 5 and month 1, right? So again, we're getting that covariance. It's assuming each covariance does not necessarily need to be the same. This is the -2 restricted log likelihood taken out to a lot of decimals. That minus 5202.977. You can see it's rounded to 1 decimal right there. So we have that, and then if you look at this, how many terms are used to estimate this covariance? So we got the 6 there, we got the 5 there, 11, we got the 4 there, 15, we got the 3 there, 18, we got the 15, 18, we got the 2 here, 20, we got the 21. Right, so we got 21 covariance parameters, which happens to be just identified right there. As we end up modeling this, you can see we lose 14 observations due to missing data, but there's our results right there. Now, we can get a lot more information by uncommenting those LS means, and then if we start looking at what's driving the month effect, we can see for whatever reason, month 1 is significantly different than month 3, 4, and 5 on average, regardless of treatment. That just jumps right out. That just jumps right out, and you can see for whatever reason, month 1, because obviously they're early in intervention, has higher average drug severity compared to, month 3, 4, 5. And then again, if we look at the treatment effect, we don't see a significant effect, but we see 1 is separating from 2, 3, and 4 significantly. It's just the others are so close, it gets at not exactly significant. But now, we don't know which of the variance covariance matrix fits this data best. So now what I'm going to do is what we saw the end of video 12. I'm going to fit this model with varying variance covariance matrices. This one, compound symmetry. This one, compound symmetry heterogeneous. This one, autoregressive. This one, autoregressive heterogeneous. This one, taupe for tauplets. This one, tauplets heterogeneous. This one, unstructured. And what you can see is I'm taking all the fit and I'm sending it using the ODS to a data set. Now, this is really how I model these repeated measures of ANOVA, these mixed model ANOVA models when I'm analyzing data. Once I'm set that the mixed effects ANOVA model is the appropriate modeling mechanism, I don't care about the statistical significance of anything in the model, right? So in this case here, when I'm doing the ODS listing close, it takes off the printout. The only thing I'm using this portion of code to is to figure out the best variance covariance matrix for the repeated measures. And here I'm setting the fit of the candidate models, right? These are the candidate models to a data set. So when I run this, I don't care about anything about the output. So from line 117, 120, I'm turning the SAS output off, and I'm not turning it back on till after I fit all these models in line 251. So all these ran. And one thing with the ODS, with the HTML on, it keeps the printout on. But the big thing here is for each model, that ODS output put all the information to fit right there. Right there. And what you guys can see is I got the -2 log likelihood, the number of covariance parameters or number of parameters in the variance covariance matrix, and the respective fit. Right now, I can go after to figure out, okay, which of these fits the data the best? Which of these, again, we're trying to get to parsimony. Which of these is the parsimonious model? So when I go here, I'm going to stack them all together. Right, so I got that right there. Right, and so, you could throw this into a data set if you wanted to. Right, you could throw this into a data set if you wanted to. But I'm going to just go ahead and look at these right here. So now we could do this iteratively. So I'm going to pull up our Excel sheet, right? So our Excel sheet, so let me just go ahead and clear this out, right? Don't worry about this. So at first, I'm going to do this iteratively. So if I look at the output, I have, there's the fit for the unstructured. Right, so I know how these are stacked. So this one's the unstructured. So the last one's the unstructured. So I'll put the unstructured fit there. I know that's 21 parameters. I'll go back to my SAS output. I'll get the fit. Just go ahead and copy it. It's 11 parameters. I'll go to here, put that there, put the 11 there, and this will give me the fit. Right? So now we know the difference is 17.6, difference in 10 parameters. So that's the p-value for the chi-square test between the different variance covariance parameters. So again, if the model with the less number of parameters, so keep these in. If a model with less number of parameters has a lower -2 restricted likelihood, it's better fitting, period. So no need to check the p-value in this case. When the more complex model, that means more parameters, has a lower -2 restricted log likelihood, we're looking to see if there is a significant gain in fit. So if the p-value is less than the alpha, then there is a significant improvement in fit, and we will use the more complex model. If the p-value is greater than or equal to the alpha level, then there is not sufficient evidence in the data to warrant the more complex model. So in this case here, the Toeplitz heterogeneous wins, right? So again, so now I'm just going to go down the list. So I'm going to compare the Toeplitz heterogeneous. I'm going to get the next parameter, the next one that has the lowest -2 restricted log likelihood. So if we look here, with parameters. So in this case here, we go to the 7. So the 7, we got 2 covariant structures that required 7 parameters. We got the 4th and the 2nd. So again, if we go back to the syntax, if we go back to the syntax, the 4th was the autoregressive heterogeneous. The 2nd was the compound symmetry heterogeneous. So remember we said, if they have the same number of parameters, the one with the smaller value, the more negative is the better fitting model. So we're going to compare Toeplitz heterogeneous to compound symmetry heterogeneous. So in this case here, we get the -5185.4. I'll copy that. That requires 11 parameters. We'll go here to the output. So in this case here, we go to the compound symmetry heterogeneous. We go here, that requires 7 parameters. So we get this as 7 parameters. And then, you could do the fill down option, which I'm doing right there. And then there's the p-value. So we could see right away the Toeplitz heterogeneous is a significant, has significant gain in fit compared to the compound symmetry heterogeneous. And in reality, if we make one more comment, right, so there's no need to compare to ARH1 than CSH better than ARH1, right? So we keep that in mind. So right now we know Toeplitz heterogeneous is significantly fitting, significant gain in fit to the 7 parameter models. Let's jump to the 6. So the 6, the only one we have with 6 is this guy here, right? So the 6 is the 5th one. 1, 2, 3, 4. That's the Toeplitz. So with the 6th one, that's this guy. So copy that. I'll go back to my Excel file. Remember, this requires 6 parameters. Then again, we got to do the fill down option. And we say Toeplitz heterogeneous versus Tope. So we see a significant gain in fit using the Toeplitz heterogeneous. So now that knocked out the next one. So the only ones we have left to compare are the ones with 2 parameters, which happens to be the compound symmetry and the autoregressive. So with these two being the same degrees of freedom, we're going to compare it to the one that gives better fit. And remember, we said the one that gives better fit is the one with the lower -2 restricted log likelihood. -5114 is lower than -5105. So we'll take this. That becomes the next comparison, right, with 2 parameters. We'll copy this, since that's our Toeplitz heterogeneous, right? So again, we'll do the whole fill down option, right? So this ends up being Toeplitz heterogeneous versus compound symmetry alone. And we see Toeplitz heterogeneous is the appropriate structure. There was no significant improvement of fit with the more complex structure for Toeplitz heterogeneous compared to unstructured, but there was a significant gain in fit for Toeplitz heterogeneous compared to the more simplistic structures. So the Toeplitz heterogeneous is the appropriate variance covariance matrix to model this data. So when we go here, we're going to go ahead and fit, in this case here, the Toeplitz heterogeneous, right? So I'm going to print out the variance covariance matrix. And I'm going to show you the variance. I'm going to show you the variance covariance matrix as a correlation matrix for patient 1, 2, and 3, just so you see what the Toeplitz heterogeneous is doing. So when we fit this model here, right, you can end up seeing we don't get an overall treatment effect. Now, I just showed you the baseline. You know, in the cocaine study, we used additional covariates that we found were imbalanced across the groups, or a priori covariates, but nonetheless, let's just take a look at the output here. So in this case here, with the cocaine study, here's the variance, here's the correlation matrix, or my fault, the variance covariance matrix for patient 1, and the correlation, patient 2. Well, I guess it's showing the variance covariance matrix first, then the correlation matrix for 1, 3, and 5, right? And then again, you can see with this Toeplitz heterogeneous, you know, it allows, in this case here, separate variances each time point, But for us, it assumes in this case, if we look at person 5, month 1 and month 3, which are 2 months apart, same correlation as month 2 and month 4. Same correlation as month 3 and month 5, right? But that becomes the better fitting model. So we have a significant effect due to month, a non-significant effect due to treatment, and a significant effect due to baseline. So we end up getting that as we start moving forward. So that's kind of cool. So we have a main effect. Now, if we wanted to look at the main effect and interaction for treatment month, all we got to do is just extend the model. And then when we extend the model, we'd say, okay, based on the available data, we do not have sufficient evidence in our data indicate that the on average treatment differences vary significantly over the 6 repeated months. And then in this case, so in this case here, so when we ran the model, one of the big things is I didn't include site in the model with the moldy site study. When I adjust for site in this model, which I should have initially, now you see the intervention effect, right? So the covariates will have an effect in it. When we do adjust for site, we see an on average significant effect due to treatment. And as we suspected, the significant effect due to treatment is the significant difference of individual drug counseling compared to the other three. So the covariates will have an effect on it. Now, some of you guys might say, well, this is a new model. Yeah, this is a new model, right? Now, shouldn't you go through the whole fit of the variance covariance matrix again? In theory, yes. In reality, if the sample sizes don't change in the model, the variance covariance matrix won't change. Won't change in the model dramatically. So you won't see any difference in fit. In this case, everybody we have site for. When you throw in covariates, they have missing observations and the effective. So if I show you guys this together, keep this in mind. This is the model without site, and without site, 2196 were analyzed. With site, 2196 were analyzed. It's when you throw covariates in that yield different sample sizes that you got to go through the whole repetitive cycle in theory. Usually if it's just a couple bodies, there isn't as much play. It's just like you said, when the sample sizes are dramatically different, then we run into an issue. But again, goofing around with the additional covariate, in reality, site should have been included from the analysis from the get-go. Again, site is not a variable that we're interested in. It's a variable that we randomized by. We had stratified randomization by site, but nonetheless, it's different types of patients at the 5 sites of the study. With the WPIC and the Penn being more urban setting compared to MGH, McLean, and Brookside. So that becomes really the key component. But again, that is a repeated measures ANOVA, or a mixed effects analysis variance, mixed model ANOVA. That's a powerful analytical model. That's a powerful repeated measures ANOVA model that you guys walk through here. Again, you guys see we use the Excel sheet to test the nested models. I have a SAS macro that I loop these through a lot of times. They're a little bit, obviously faster and does all of this mathematics for me. Obviously, you guys, you guys don't have that in front of you right now as we're doing that. But again, the Excel sheet does it. And I think when you guys are doing this at the beginning stages, it's kind of good to see that iterative improvement and fit. Let me take you guys back to the slides. So that's the end of this extra one. But if I go to the beginning, it discusses repeated measures in HLM. What I want to show you now is extra 2. And if I go to extra part 2, you guys will see this. So back in 2014, I was invited to give this tutorial of longitudinal data analysis, introduction longitudinal data analysis, at this conference that was held in Philadelphia. ABCT, as you guys know, a lot of my history has been working with psychological data, and this is one of the big psych conferences. One of the big psych conferences have these things called SIGs, which is special interest groups. And the statistics SIG invited me to give this presentation. As you guys look at this, this goes on for 176 slides. So you could save it for your use at your leisure. And so if none of you guys take the LDA elective, which is STA 533 in the program, you could use these slides as an example of it. And if you guys go, you'll see I show a lot of information on how to do longitudinal data. And one of the big things I introduce you to first is this thing called the hierarchical linear model. And then with the hierarchical linear model, I end up showing you guys, with this hierarchical linear model, how to analyze it. Now, with this special interest group, they were really interested in laying it out in SPSS, and I show them a lot of the screen captures with the SPSS. So again, keep that in mind. Show you guys one more thing too. If I go to my webpage on the WCU webpage, if you guys go here to this webpage right here, you'll see the PowerPoint slides I used right there, if you ever want to get back to them. And then you'll see me with my Super Bowl 39 shirt on this page. So me with the Super Bowl 39 shirt is where you guys see the slides, as well as a zip file which contains a lot of my one of my big papers back from 2009 and all. But again, a lot of that can be pretty helpful as you guys move on. So again, you guys look at this. It goes through the HLM modeling framework, a lot of screen captures and how to do it in SPSS, and changing how to look at the models a little bit more flexibly, looking at data in terms of, instead of linear time, log change over time. Looking at the effect of polynomial models in this example, missing data. And then if you guys get here, we start looking at the general linear mixed model, and namely the mixed model ANOVA model that you guys just were looking at. As we looked at some of the, and again, we hit some of the big variance covariance matrix. There's a whole bunch of others as well, but I think I showed you guys really the big ones that we use. So again, this is the mixed model analysis of variance example we just looked at, that I think is pretty good. And then, the end of it, we don't get into how to deal with non-continuous outcomes, 3-level data, bioequivalence, and power and effect size derivations, but they're topics to be discussed in a higher level course. But this was an example with the mixed model ANOVA for STA 513. This is the end of the video, so I thank you for your participation, your attendance, and hopefully this information is of use to you guys as you get down the road, and I'll see you in the class sessions, in the live class sessions. So thank you so much.